Okay, so today we're going to discuss the last application in this course at least. I need your attention. Thank you. The last application which you will see in this course, application of eigenvalues and eigenvectors and diagonalization. First significant application we discussed with you last week, it was the application to discrete time systems, where you can solve every discrete system explicitly with the help of diagonalization and with the help of powers of matrices. Very similar analysis can be done when you do continuous time systems or continuous dynamic systems. It's a systems which are governed by differential equations. That's a typical system I'm going to spin my today's presentation about. So imagine you're facing a task. Imagine you're facing a task of finding two functions of a continuous time parameter t, which are subject to two differential equations, like this. With the help of eigenvalues and eigenvectors, we can do this in a very systematic way, in a very structural way, and I'll show you how to do that. First, you convert your system into a vector form, very similar to what we've done to the discrete systems. We give a vector language to the problem. So I'm just double checking. I want to double check if I'm recording. Yes, I am. So first, here's the function xj here is a function of continuous parameter with values in r, j here from 1 to 2. So you introduce a matrix of these coefficients, 3, -2, -1, 2. Here's my matrix. You introduce your vector function x in the boldface, and then your system, this system, in the vector language becomes this. And then your system in the vector language becomes this. And now I show you how you can see the solution to such a system in a vector language, and how much structure you can see in this solution with the help of eigenvalues and eigenvectors. In order to show you this structure, I want to draw some parallels with the numerical systems. If you look at the system like this, A here is a matrix, isn't it? It's a matrix of size 2 times 2. But if for a second you assume that A is a number, or a matrix of size 1 by 1, the system will be of this type. This is the numerical analog of what we're looking at here, where x is no longer a vector, where A is no longer a matrix. Okay, and I would like to, I will search for the ideas how to solve this. I will search for these ideas here. In the treatment we have for the numerical differential equation like this. If it's a regular numerical differential equation, we know how to solve it. It's something you studied in calculus this semester quite extensively. It's the equation with the separable variables, isn't it? All you do, so A, in this case A is just a number. All you do, you separate your variables. That's a separation. All x is on the left hand side, all t is on the right hand side. It's a very easy solution. Left hand side integrates into log. Right hand side integrates into a linear function plus a constant. Then you put everything into exponential forms, and here's your solution. This is very well, which is you've done quite a few differential equations like this during this semester. I don't expect any questions here. So after realizing this, I'd like to see whether this something like this can be done here. We cannot do separation of variables here, of course. We cannot divide by x when x is a vector quantity. We have nothing of this sort, so we cannot repeat the same steps here. No way. But we can try to model the answer. And by saying so, what I mean is this: for the exponential function, we have a Taylor series representation, don't we? We have this representation. In sigma terms, again, it's another thing which you've done quite extensively this semester in calculus part, and it's a good thing now. I like it because now these two, the algebra and calculus, they sort of meet right now. I'm going to borrow interesting ideas from calculus. That's the idea. It's the second idea from calculus. First idea was the way we solve this differential equation. Second idea is this Taylor expansion or Taylor series for exponential function. And here's an interesting idea now. Yes, I can't do anything like this when I look at the system of this type, but I can certainly model this. Because the right-hand side in this expansion, it only manipulates with powers. And unlike exponentials, unlike logs, unlike divisions, powers I can do with matrices. So my conjecture will be, what if I take a function, vector function, you see, both ways. What if I model my function like this? If I take the infinite series, I copy the coefficient from here, t n factorial, you see. But the a, little a, which went in, which is number in this context, in the context on the right-hand side of my slide, I now replace it with matrix power. A is a matrix in this context. On the left-hand side, on the left-hand side, the context of A is matrix context, and times some C. C is the R2 vector, constant vector, independent of T. So all T dependence is here. It's a very interesting idea. It's actually ingenious idea. Whoever come up first with this idea, he was a really insightful mathematician. So I just take this as a candidate for a solution, and I'll show you now that this actually works for this matrix differential or vector differential equation. All I need to do, I need to take this formula, I need to sub this formula in here and see if it works, left-hand side, right-hand side. Here's my substitution, look at this. Derivative of x, this is a vector function, so it's a function which takes values in R2. It does so because an, it's a 2 times 2 matrix. When you multiply by a constant c vector, the c vector, the c, it stands for the c1 constant. If you want to see the analogy where the c came from, is this c1 constant. It plays the role of this c1 constant. A power n, it plays the role of this a, little a to the power n. The rest is just copied, literally. So here's my testing that this is indeed a solution to this differential equation. I sub in, on the left-hand side, my formula for x. It's a substitution. I need to differentiate this. The only dependence on t sits here. I can take this differential operator and apply only to every term individually, and this is a constant. This is independent of t, so I can just ignore this. So here's my individual differentiation. You see, I just pull this d by dt and apply it only to the coefficient. This is a just numerical function. We know how to differentiate that. It's a power function. When we differentiate that function, we end up with this. I mean, the derivative of this function is like so. I started my summation from 1 this time because the 0 term, which is a constant term, it will disappear after my differentiation. And I factored this an into an take 1 and 1 extra a, which I pulled in front of my summation. All I need to do now, I need to just change the index of summation. I need to make it index, I need to introduce new index k, which is n take 1. If I introduce this new index here, the expression will become like so, and this is exactly the formula for x. Look at this. So we finish with ax, we finish with the right-hand side. That's the whole idea of the solving of when you solve the continuous dynamic systems in the matrix, in the matrix or in the vector form. You just borrow idea from the numerical case and you introduce this construct, which delivers you a solution. It doesn't yet mean it's easy to compute this construct. I mean, if you think of it, if you just look at this matrix and you just ask yourself how to find such a series which involves infinitely many different powers of such a matrix, it doesn't look like an easy task, but at least in principle we have this formula which delivers the solution. So that's something which I now frame as a theorem. If you have a differential equation in the vector form, like this, then the solution to this differential equation is delivered by this infinite series formula. The only alteration I made in comparison to this, I replaced my c vector with the x of 0, which is just emphasizes the role this c plays, because if you substitute 0 in place of t in this function, every term here in this series will be 0 except the very first term when n is 0. And this very first term will be c alone. So what I'm saying is this. This formula suggests that the 0 value of the function like this is c. That's why here, to make it more explicitly, I just replace it with x of 0. Okay? So this is the whole idea. Actually, that's the idea which covers every system like this. It doesn't matter what size of the what is the size of the matrix in your differential equation. It can be of size 2, 3, a million, any matrix. For any matrix, this formula will deliver a solution. So on the principle, on the structure side, that's all we need to know. For the rest of today, we're going to study how actually we can compute this expression in the efficient way, and that's where the eigenvalues and eigenvectors will pay off. One hint towards this, towards thinking eigenvalues and eigenvectors comes from the fact that when we compute powers of matrix, remember, diagonalization helps a lot to find powers of matrix. So at this stage, we have high hopes that not only powers can be easily computed when you have diagonalized the matrix, but also this expression also will be easily computable in case your A is diagonalizable, and I'll show you that this is indeed true. Any questions in relation to the way we solve vector differential equations of this type? Okay, so my next slide is called matrix exponential, and I think the slide we just saw warrants such a name with no questions. What I'm going to do is this. I'm going to take a matrix of size k, square matrix, and I'm going to call this expression we just introduced. You see, I just dropped the c vector from here, which doesn't make much of a difference. Now I'm just looking at the matrix part of that expression. I just copied this from the way we expand numerical exponentials, but I replaced numerical A there with a matrix A, and I have the full right to call this expression matrix exponential. Just because this is modeled from the numerical exponential. What I would like to discuss now, how to effectively compute such a matrix exponential. Of course, we expect this to be a matrix of size k, because every individual power is a matrix of size k. If you sum them, even if you sum infinitely many of such matrices, the result will be a matrix of size k, square matrix of size k. That's the place where diagonalization helps enormously. So let's just assume that my matrix meets a diagonalization. So we have a representation for my A in terms of P and D, where P is a diagonal with eigenvalues on the diagonal, and where D is a diagonal, with eigenvalues on the diagonal, and P is a matrix composed of eigenvectors as columns. This boldface V1, V2, Vk, they are k tuples, they are eigenvectors for my A matrix. So we assume we have k of them and they are linearly independent, so this P is indeed invertible. So this factor here makes sense. So we have a full diagonalization. When you have such a setting, finding such a huge series, even though we manipulate with matrices here, becomes easy task. Look at this. So if I go after this matrix exponential, I just replace every matrix power with the formula we have for the matrix power when we have a diagonal, something we discussed with you on Thursday last week. That's the formula we discovered with you on Thursday. If you have diagonalization, then the nth power of the matrix can be delivered through this. So where you take to the nth power only the middle factor, the diagonal factor, you don't touch p. So that's what I just did. I replaced this an with the formula for that. Now I will take it even further. When you take diagonal matrix to a power, all you do, you take diagonal entries to that power, isn't it? All of this lambda 1, lambda 2, lambda k, I'll take them to the power n. Here it is. Sum, this coefficient, exponential coefficient, my p. Now I replace my g with what I have for g to the power n. You see, I just took to the power n every diagonal entry of my G matrix. Because it is this easy when you take powers, when you compute powers of a diagonal fact or diagonal matrix. My next step will be this. If you look for the expression, just this last expression, you'll see my n, the index of summation, it appears only here, and it appears only inside my diagonal matrix. It's nowhere else you can see this n. P is n free, and P inverse is n free. What I will do now, I'll move this summation and this factor here in every diagonal entry. When you scale a diagonal matrix, you scale every term on the diagonal. When you sum 1, 2, 3 or infinitely many diagonal matrices, you just sum the corresponding diagonal entries. So here we go. You see my summation and my factors, they went into diagonal entries. My summation and my factors, they went into diagonal entries. At this stage you can appreciate this notation, diag. If I didn't have such a notation, if I need to write this huge square block every time, which will be filled with lots of useless zeros, the writing would be a lot more inflexible and harder to read. But with the diag notation, we just expose only the meaningful part of the diagonal matrix. All the zeros we don't put them explicitly on a slide, even though of course in our heads we remember that there are zeros there. Each of these diag is a square block, square matrix. Well, the final step will be each of these terms now. It's a sum of numbers. It's no longer a sum of matrices. It's a series which consists of numerical terms. And each of this sum is in fact exponential Taylor series for normal numerical exponential function. I can replace each of this infinite sum with this. This sum, it's a representation for this exponential, et lambda 1. This sum is a representation for this exponential. This is a very far reach actually right now. You can't even imagine how far we moved our knowledge of matrices and our skills with doing with matrices with the help of diagonalization. Look at this. We were able to find the really huge infinite series which involves sums of the powers of matrices into just two matrix products. This is one single diagonal matrix where on the diagonals you put the exponential functions, numerical exponential functions with eigenvalues in there. I don't know if you just get the whole greatness of the eigenvalues and eigenvectors methods and diagonalization, but it's a huge advantage. I'll show you one example how to compute that, but even now I think it should be quite transparent how important and how much you can do with diagonalizations when you have a matrix diagonalized. Like I said, unfortunately, not every matrix is diagonalized, and when it is not diagonalized, there are still methods how to find these exponential sums with matrices in them. There are methods. Some of you who will continue the study will learn them one day, and you will appreciate the simplicity diagonalization gives you. Okay, I'll show you. Any questions? I'll show you one example. I'll take this matrix A, this 2 times 2 matrix from my very first slide, and I'll compute this exponential of that matrix. in full on my next slide. Look at this. Here's my matrix. Here's my matrix. This time, because we haven't done such a matrix before, I need to compute every component of the spectral analysis. I need to find all of the eigenvalues, all of the eigenvectors. But given that the size is 2 by 2, it's not that hard. So first I make the observation that if the sum of the eigenvalues, it's an efficiency trick we discussed with you once, that for the 2 times 2 matrix, you don't need to go characteristic polynomial way. Most of the time, you can guess the eigenvalues, and that's how you do guessing. You make the observation that the sum of the eigenvalues is a trace of the matrix, which is the sum of the elements on the main diagonal, 5. Product of the eigenvalues, it's a determinant, which is in this case is 6, take 2, 4. So these two relations, they allow you guessing. They will let me guess the values. One value is 4, and the other value is 1. For each of these values, now I will compute the eigenvectors. So for the value 4, I need to consider this matrix, A take 4 identity of size 2. That's my A. This is the matrix A take 4 identity. I subtracted 4 from here, which is -1, and 4 from here, which is -2. We ended up with a matrix with nullity 1. I need to choose a vector which is in the null space of such a matrix. A good choice will be this vector, 2, -1. This is a vector in the null space of my matrix. So this is the eigenvector. Similar analysis for the second eigenvalue, 1. Now this time I do this matrix, A take identity of size 2. That's the matrix. I subtract 1 from 3 and 1 from 2. So it's a 2 and 1. Again, you need to find a vector in the null space of this matrix. For the matrix of size 2 times 2, it's a very easy guessing. That's my guess, 1 and 1. It's a good choice. So the spectral analysis is fully complete. We have 2 distinct eigenvalues. We can be now absolutely sure that the resulting eigenvectors are linearly independent. It's a general result we discussed with you once. That means that I have full diagonalization. These are the elements of my diagonalization. This is a P matrix. This is a P inverse. Determinant of this one, 2 plus 3, plus 1 is 3. It's 1 and 3. Now I swap the diagonal entries, 2 and 1. They swapped over. And the other ones, they just got the extra negative next to them. That's how you compute the inverse for the matrix of size 2 by 2. G, I didn't put G explicitly on my slide, but G is just the one, it's a diagonal with entries 4 and 1 on the diagonal, in this order. 4 is first, 1 is second, because eigenvector for the number 4 comes first. Now I can do exponential. Exponential, so this infinite sum which represents the solution to the differential equation from my first slide, the differential equation which involves this matrix, all I need to do to find this infinite sum, is compute this. It is exactly the prediction from the previous slide. I take my P inverse, and I squeeze in between diagonal matrix with the entries on the diagonal field with the exponentials involving these 2 eigenvalues. You can't deny this is it's an absolutely great result. I mean, it's a very clear advantage of having the diagonal matrix, matrix diagonalized. Infinite sum, once again, which involves infinitely many powers, reduced to 2 matrix multiplications. In fact, one of these multiplications is also easy because you multiply a matrix by a diagonal factor. That's another type of multiplication which is very easy to execute. So here we go. If I multiply, actually this is a substitution of all of the components. So I just replace my P here and P inverse from here, 1 on 3 went to the front. I need to multiply this out. When I multiply these two together, like I said, all I need to do, I need to multiply the columns by the corresponding exponentials. Here it is. See, first column multiplied by this exponential, second column by this exponential. The second factor, the last factor, I just copied it. Now the last matrix, it's the only matrix multiplication which requires the full algorithm of matrix multiplication. And here it is. I insist that this last product is this row by this column. It's 2e for t plus et. I'm happy with this. Second entry is this row by this column. It's negative 2e for t plus 2et. It's from here. I'm happy with this. I'm just double checking my own computations. This row by the first column. That's fine. And the last one is this row by this column. It's plus e4t and 2et. That's right, 1/3. I kept it in front. This is the result. This is a matrix function which represents this matrix exponential, the one which we need to solve the differential equation on the very first slide. Infinite sum, infinite series with infinitely many different powers of a. We can just compute it down to this one single formula with the help of diagonalization. Any questions? In fact, it's getting even better. Well, and I'll show you what I mean by that on my next slide. But first, any questions in relation to the way we do matrix exponentials? It's getting even better in a way that actually for the system on my first slide, you don't even need this matrix exponential. I mean, from a structural point of view, it appears quite clearly in the general solution, and now we know how to compute that. But from the practical point of view, now I'll show you a shortcut which helps you to avoid all of these steps. So in terms of, from the practical point of view, if you solve a system, this matrix system from my first slide, you can make it even shorter than this. Look at this. It's my next slide on continuous time system. So look at this. Continuous time systems number 2. So we have a system like this. It's a matrix system. A is a square matrix. X here, it's the vector function. X here is a vector function, so the function which has a numerical continuous parameter, time parameter, and values taken are in k tuples. So this is my differential equation. We know now that the solution to this is given by such dynamic. You need to compute this matrix exponential. You need to introduce your initial conditions, C, or constant, which represents the initial condition. But in principle, that's how you solve it. And not only this, we also have now the computational machinery to find this exponential. It's not a universal machinery. It only works when matrix is diagonalizable. But the good news for you is that in this topic, every matrix will be diagonalizable. I mean, when you need to find the matrix exponential. However, this slide will show you that actually, in order to find solution, you don't need this matrix exponential fully computed. Look what happens. So again, we just start off with the assumption that A is diagonalizable. So D is a diagonal with eigenvalues on the diagonal. P is the one which consists of eigenvectors as columns. All of these VKs, V1, V2, VK are K tuples. That's the setting from my slide before, from the slide where we come up with the formula for matrix exponential. Now I'll show you the shortcut, one shortcut which is available to you. Okay, so, right, so formula for the matrix exponential, it is this one. Remember, when I use colon and equal sign, it means that this symbol is defined to be this. Now we know that the same thing can be computed like this. That's another thing we discovered, that you can just take the diagonal matrix with exponents on a diagonal, exponents with eigenvalues in them, and multiply by p and p inverse on both sides. That's how you compute this matrix exponential. This is again something we established on the slide before. Now I'm going to use this. I'm going to take this expression. I'm going to put it in here and see what happens. I'm going to sub this whole thing in here, and I'll try to show you the shortcut, which in fact will let you avoid doing these two matrix multiplications. So in fact, for your exponential, when you do dynamic systems, you won't even need these two matrix multiplications. Look at this. So I use the whole thing here on the right hand side and I sub in here. So I multiply by c. Here's a substitution. Look at this. My xt solution is p diagonal factor, p inverse, and then here's my c constant. C constant in boldface because it's a vector constant. All right, so let me just recall the first thing I'm going to say is that the P is the one which consists of eigenvectors as columns. A while ago, not so long ago actually, we discussed with you what happens when you multiply two matrices and one of them you keep the column structure in it, right? That's exactly the case here. P is the one which consists of v1, v2, vk as columns, and you multiply it by diagonal factor from the right. All you do in this multiplication, you scale every column in P, v1, v2, vk, by the diagonal entries here. That's what I've done here. First column v1 scaled by et lambda 1. Second column similarly gets scaled with et lambda 2. Last column gets scaled with the et lambda k. I've done this multiplication, but it's an easy one. It's a diagonal because it involves diagonal factor. The next observation I'll make is that this factor, when you look at it together, it's just a vector, isn't it? P inverse is a matrix of size k, square matrix of size k. C is a vector. It's a k tuple. When you multiply a matrix of size k by the k tuple, or by a column vector with the size k, this result will be a vector or a column vector with k entries. And I will give names to these entries, little c1, little ck, no longer boldface. So the last effort you need to make when you think about matrix multiplication, this last effort, when you think about this cross, listen to this. On the left-hand side, I have a matrix of size k, square matrix, and I have a column structure explicitly given in this matrix. On the right-hand side, I have just a column vector, one vector, and I have names to the components of that vector. When you multiply a square matrix by a column vector, the result will be a vector, as expected. This is supposed to be a vector. Look at this. But can we come up with the explicit formula which connects this vector with these columns? If you think the way we do matrix multiplication, the answer is yes. This product will deliver just the linear combination of these columns with these coefficients. That's the last effort you need to make in order to see the shortcut. It's the last effort you need to make in order to see the shortcut. This matrix product, this cross, will deliver a linear combination of the columns in here, in the left factor, with coefficients from this column vector. See? C1, C2, Ck. And here's your shortcut. When you solve a dynamic system like this, even though structure-wise the solution is given by exponential, you can jump straight away down here. The solution will be a linear combination of eigenvectors of your A matrix with coefficients, with some coefficients which can be determined through initial conditions, of course, and exponential functions. Exponential functions with eigenvalues as factors in those exponential factors. Yes, that's right. For this to be true, you still need the matrix to be diagonalizable. So you still need to have k linearly independent eigenvectors. K is the size of your matrix. If you have less than this formula is no longer suitable. As the exponential method is no longer suitable because exponential method is suitable. The solution still will be given by the exponential formula. It is just no longer you will be able to use this one to find your exponential, because if your matrix is not diagonalizable, this formula is no longer valid. So if your matrix is not diagonalizable, if you don't have enough eigenvectors, then from the structural point of view, you still have a solution in exponential form, which is given by this formula, but you no longer have the means to find this formula yet, to compute this expression yet. And that's why you cannot rely on this shortcut, because this shortcut, in the way we derived it, it relies on this formula. So you will use this shortcut without doing this explicitly, but back in your head, you have to remember this shortcut. You can only use this shortcut if the matrix is diagonalizable, so it has enough linearly independent eigenvectors. Any questions? Yeah, well, I'll finish the example now from the first slide today. Yes, I'll finish this example, so look at this. Unless you have any questions in relation to the shortcut, in the general exposition of the shortcut. So here's the continuous dynamical systems or continuous time systems. It's the same thing. So here's my system from the slide, from the first slide today. X were functions, numerical functions, xj were numerical functions. So on the first slide, we converted the system into matrix form. I introduced a matrix A. I introduced a vector function, x boldface. We know that the solution to the system now is given by the exponential, by matrix exponential. But if I use a shortcut, I can use a shortcut because I know that this matrix has two eigenvalues, two distinct eigenvalues. So I know that the eigenvectors associated with those two eigenvalues are linearly independent. You can even see this explicitly. This information we computed with you 2 slides ago when I did matrix exponential example. So all I need to say now, is just the general solution to this system, or the general solution to this system the general solution to this vector system is given by this formula. You see, I took my eigenvectors here, I introduced exponential factors with eigenvalues in them, and took constants which can be found through initial conditions. And that's all there is to it. That's a shortcut enabled by our matrix exponential analysis and by diagonalization computation. Everything just reduced down to these few lines. I mean, of course, there are some computations behind this data, but when you have this data, this is a general solution to your dynamic system. Any questions? Are you sure you don't have any questions? Well, this is the last thing I wanted to discuss with you. We finished everything we needed to discuss. There won't be any lecture on Thursday. Yes. You can have a free time. So remember this. I congratulate you all on this wonderful journey, on finishing this wonderful journey. I wish you the best of luck with your examination, and best of luck with the rest of the topics in this unit you're going to take. Thank you very much. We finished. Thank you.